This is, so what you just saw is Jim will present a progress for separating reflection data from reference wave, including ground wall for onshore and for deghosting. The data promising code is a year from now, but if we can do a field data test prior, we get that code delivered. But we're not going to do it before we test on field data. So we're giving a date that allows for either through her internship with Schlumberger this summer, a second internship, or some other way to get a field data test. We don't, we don't deliver a code that has not been field data tested. So this is the second part of the green sphere where it's not for Wayfield separation, but for Wayfield prediction, as you mentioned. So wave theory methods for seismic imaging, they have two components, a wave propagation idea and an imaging principle. And it's a broad subject, and we're not going to cover, and there are many experts here, and many pioneers who make some comments, but we just want to try to make a point of what we feel is something new, and could be interesting to explain what we plan to deliver within this project. So John Claerbout, famous 1971 paper, described three imaging principles: an exploding reflector model, time-space coincident of up and down waves, and the third, predicting a source-receiver experiment. So predict what a source and receiver would experiment would be at a coincident position in the subsurface, and ask for time equals zero. We're labeling this Claerbout 1, 2, 3. That's just our labeling. There's an extension of Claerbout 3 that Stolt and his colleagues, Clayton, Benson, and ourselves, extended that imaging principle to allow for not just structure and an angle average reflection coefficient. In other words, if you have a source and receiver that are proximal at a point in the Earth, and you ask for t equals 0, and then if you separate them, you're going to get 0. If you ask for t equals 0, then it needs some time. But that's a singular function. In other words, it only lives, or in some way, being very rough here, at one point at x is xh is 0 and t equals 0. Well, what's the nature of the singular function? If you examine it, you get angular dependence. And it's very sharp, just bandwidth limited in space-time, but in Fourier, it's spread and easy to, and that's where Stolt is. But it's, we'll often call it Claerbout III, just including that extension, the amplitude analysis. I just wanted to make that statement. So we're in this recent work, we are not progressing those imaging principles. What we're progressing is a way to arrange for that experiment. The experiment for 3. Under different circumstances than is currently available to predict that experiment. So I'll try to make that a little clearer. So time and space coincidence of up and down waves, this is extremely popular. It's become almost synonymous with the word migration. And there's been different, when Dan Whitmore invented RTMs at Apple many years ago, there was a form of that. There was an overlap when you do zero offset version and then extend it. But the main and historic contribution was go back in time, not space, because they're not the same. You have a diving wave. You go back in time, because everything before Dan and his colleagues was back in space. One way, yes, in space. And for a diving wave, for example, space and time, as time goes in one direction, space never doesn't necessarily go cone, it can get bigger and then smaller, yes, as time goes in one direction. So that, basically, the way that idea has been implemented is in some form of time-space coincidence of up and down waves. We have some other world champion people here, Yu Zhang and Sheng Zhu, so somewhere. Sheng Zhu wrote a very famous set of papers on this idea, Claerbout II, for one-way waves, and where they added a component where they gave a model for the reflection data in terms of the geometric opposites reflection coefficient, yes, and outputting that. I'm just mentioning some different, this is again a vast subject. There's a book we stole recently that discusses it. We're not going to go through that book here. That book is about this kind of thing. One of the advantages of this three, that principle by itself, forgetting how you get there, we're going to discuss that in a minute, yes? But if you actually have a source and receiver at some place in the Earth predicted, then you can make a plane wave experiment there by Fourier transforming over a source at different angles, and you can get a specular plane wave reflection amplitude, but you made a plane wave experiment at that place. If you have a specular reflector, then you have a specular reflection coefficient. If you have a curved reflector, you will get a plane, and you will not get specular, you will get distribution. If you have a pinch out, you get a plane comes in, a non-plane comes out. That's all accommodated by Claerbout III extended. In scattering theory, you get a point scatter model, so you can do structure and inversion in the presence of. So there's two advantages of this in our view, two unique advantages. One is when you have specular reflection, yes, it gives you plane wave reflection coefficient versus geometric optics. Why does that matter? Because all of our amplitude analysis, you look at popular machines, yes, it's plane wave. It's not geometric optics. And you'll see examples with the difference between geometric optics and plane wave reflection coefficient. And if we're treating reflection coefficient with nonlinear activity, yes, you understand, to do things, yes. So for specular, Claerbout III gives you the opportunity to, with that experiment there, to make a plane wave experiment. To make a plane wave experiment. First you'll determine where there's something, and once you're where something is, you can make an experiment and then determine whether. So how do you know it's specular or not? You don't have to know. The data knows. You can see the spread in outgoing wave number. If it's peaked around somewhere, you're getting, let's say you have some normal to a specular reflector, you make some Fourier come in, yes, and then you look at your outgoing K geophone, and if it will be peaked around some angle with respect to a normal, yes, giving you specular. So you have some threshold. If it's spread, then you know you have some curvature. You understand? So but you can automatically, these what we call point scatter models, assumes a point, and if the point constitutes part of a specular, you'll get that. And if it doesn't, you get what points do, like here. So yes, like you don't want to do a geometric optics imaging at a pinch out, yes, which is an important imaging point, yes. So all that is achievable naturally through. So more discussion of all these differences is a whole topic by itself. We're not providing that. You'll see some because we want to explain some of the strengths of this compared to other. Yes, you see some talks on that. But what we're providing, so those differences are there for one-way waves. Yes, differences. what we're providing is the way to get the experiment under conditions where you have two-way propagation. You know, going through a reflector. If in your volume you have waves going up and down, yes, you have two-way propagation in that. So let me get clearer about that. So what we're providing is a new way to realize this experiment when you have waves that are moving in two directions. Whether they're multiples, or you're going to a sharp change, a sharp boundary, or yes, or you have diving waves, yes, and you want the benefit, of what that experiment will give you, yes. What the benefit that experiment will give you is not what we're contributing now. Understood? That's yes, we're just arranging for that experiment where it hasn't been arranged before. So the other point is, if you, there's something very definitive in Claerbout III. You have an experiment at a point. You bring a source and receiver there, and it asks the question. When they're together and you ask for t equals 0, does it have a non-zero value? In other words, if you have a source and receiver here, and the reflector is here, and you ask for t equals 0, you're going to get 0. There's no reflector at this point. The reflector is here. So until this is here. So you get when that experiment is at the point, the answer is yes or no. There's no summing of possible images as you'll see in Kirchhoff and versions of Claerbout II. This is possible, and this is possible. And you coherently look for coherent sums of what might be images. Yes? That's a very different kind of activity. Understood? So you'll see the consequence of that, and some of that, to motivate you to be interested in what providing a Claerbout III experiment in a two-way world could be. Let me just say straight out, what we're going to deliver is very different than this. What we want you, because there is expertise here in velocity analysis, anisotropic velocity analysis, depth imaging capability. We're not going to try to compete with that. If sponsors are interested, we can work with you. How do you arrange, yes, within your machinery to output that kind of image? That we're not going to produce a code for you. You understand? We don't have, I think it's clear, yes? Well, we'll work with anyone who's interested within the sponsor group who has velocity analysis capability, yes, and imaging capability to change, for example, a current RTM into one that would do that kind of structural and amplitude benefit. Okay? That's the only project that we have with that kind of output, because it's not our mainstream activity. Okay, so this is what we were saying. Claerbout III provides, once you have an experiment, that you have the experiment at any point. In other words, first it decides, is there an image? And if there's an image, then you have the opportunity to make a plane wave experiment there. That's what so for specular, you get a plane wave reflection coefficient. What Zollfritz and Borfeld are talking about, yes? Everybody understands that point? And then for non-specular, it gives you, for this, a more general imaging model, structural imaging model, which doesn't assume that the generator is specular, so it allows you to map it and identify changes through it. Okay. This is a typical current RTM. We'll be talking a lot about this. I think this comes straight out of one of Dan Whitmore's papers. Okay. Same notation. Okay. This is the source field, this is reflection data, this is the complex conjugate. Yes. This is typical. We'll compare this to what Claerbout III would tell you to do. You understand? Where So we're going back to Green's theorem to talk about if you want to predict what an experiment is. Well, there's a theory that says, given measurements on a closed surface, how do you predict the wave inside, yes? The very important message from this group is George Green was not talking about this. He was talking about a closed surface. Okay? So we often forget that. You think that somehow it's this. You got to start with a closed surface. And then, so we went through all this. So you have this kind of story here to get the feel inside. What are we talking about? This is a receiver inside now, based on measurements on the surface. This guy, we assume, is not here, meaning alpha, we assume is 0, that the reference velocity and the actual velocity agree. Remember what alpha means, the difference between C of R and C0. We're in migration, we're assuming inside the volume we have information. Understood? So that this term is not here, so we're in that term. So from that term, we want to predict this. Okay, for the scattered wave, that's just saying it just cares that alpha is 0. In other words, a reflection wave. So this is the story. You want to get R in the volume. Predict what a receiver will be in the volume from receiver measurements on the surface. So here you got a volume, here you got a source there, here's some closed volume, here's an upper surface, a lower surface. You can show that if in this volume the wave is moving up, and it doesn't have to be straight up, but up, in other words, it has a certain sign to its vertical wave number. Yes, you understand? It's not turning, in other words. If a wave is moving up, then you can show analytically that if you choose an anti-causal Green's function in this integral, here you have a closed surface. If you have a wave that moves up, you can show analytically that if you choose an anti-causal Green's function in here, that the upper surface contributes and the lower surface does not. If you have a wave that moves up and you want to predict from measurements around, all you need is the measurements on top. The way you can understand that is this wave is moving up. Anti-causal tells you where it was from where it is. Yes? And here, where it was would be under, you know? But that's only for going one way, yes? If you take an anti-causal Green's function in some region, and then you say, well, it's one way, so I'll only need the field, yes? Not the derivative. So you arrange for the Green's function to vanish on top. You call that Dirichlet. Understand? In other words, it's anti-causal and it vanishes on top. Why am I saying that? Because in this integral here, on top, in other words, what I just said is, if the wave moves up, anti-causal just needs this guy on top. But I only want to need this on top. Understood? So then arrange not only for this to be anti-causal, but to vanish on top. That you call that imposing a Dirichlet condition on the Green's function. If you do that, you know what you get? Stalled prediction, phase shift. You get a shift. You understand? Something we're familiar with. I'm describing it in Green's theorem terms, yes? But it all because if you look at it in, just to give you some quick, we're in the elevator, we have to explain it. If you look at 1D normal incidence, an anti-causal Green's function looks something like this. Just to keep it simple, if it's to be vertical wave number like that. Yes, this is what an anti-causal looks like. So, and so if you differentiate it, again among friends, this guy's going. Yes. let's say Z is where you're predicting, Z prime is the measurement, so Z is bigger than Z prime, and you get rid of the absolute value, yes? And you differentiate it, you are going to get just, this guy's going to go away. So the derivative of the Green's function is basically a shift. Yes? And making it vanish doesn't change that. So you get stole. Stole is for up wave, anti-causal, you go down. Yeah, okay? So that's what that other slide says. So if you do this P with this anti-causal, and yes, brings the source down, and then bring the receiver down with reciprocity, and you get stole migration. Yes, so stole migration is a one-way wave realization of Claerbout III. You bring the source, the receiver down, bring the source down, ask for t equals 0. You want me to write that? You know, you do the shift. That's the shift. The shift, when you do the shift, you have it in the Fourier domain, kg, ks, omega. When you do the shift, e to the minus I square root plus square root z. This guy brings them down. Yes? When you Fourier transform over this new variable, so changes that to a new variable, then you are that dkz. In other words, this already takes it to z for a plane wave. When you do dkz, you're really doing d omega. It's a Jacobian wave. So that is the imaging condition. So Stoke is, all I'm saying is pre-stack Stoke is Claerbout III realized in a homogeneous medium where waves are just moving up that you're trying to bring down for this experiment. That's all. So now we're going to say, how are we going to arrange that experiment when the waves are not moving up? That's the only thing we're adding. Yes? So now we have waves moving up and down. Up and down could be guiding waves, yes? Could be going through a reflector, and you want to bring the wave under, yes? You want to image beneath, because you want to go further, yes? You're at top salt, you want to go under, yes? You get, okay. So as long as in the volume you have waves moving up and down, and you want to predict. So now, what you have to, if you want to arrange, it's very simple what we've done. If you want to arrange, our objective is to make that, pick a G0, pick a G, remember we said any G0 will make, as long as there is a surface integral, any G0 will make the actual field. When you put anti-causal here, you made that wave go back, but you didn't predict an anti-causal wave. You predicted the wave where it was. You didn't violate causality or something, you understand? This is, when you do Stoke migration, right? You do a shift, that's not an anti-causal output. You just took a causal wave and found out where the causal wave was. Yes? The was made it with the anti-causal Green's function. But the wave you predict is real, it's causal. So the point is, what we want is where we can't assume the wave is moving up, how do we arrange for this to predict a wave inside the volume where I only need measurements on top, because that's all we have seismically. That's it. So all we do is we arrange for the Green's function and its normal derivative on the bottom, both to vanish. That's all. Arrange for the Green's function and its normal derivative to vanish. When you do that, for two-way waves, we have papers that show you for multiples and so on. You understand? You will predict the experiment. Yes. That's all we contributed, and then using it. You understand? So once you have the experiment, you're back to the differences you would have with one-way waves. The structure and amplitude and so on. We're not adding anything to that. Is my point clear? Okay. So that's what a double, in other words, this is, you have to do an integral over receivers and then over sources. It's sort of a double Green's theorem. These are all surfaces on top. So what do? You bring, you predict the receiver, then you do reciprocity, then you bring, yes, do it again, integrate on the sources. Yes, like that. That's all. So the difference between this, so here, when you do this for one shot record, this time-space coincidence, when you do it for one shot record, you'll see output soon enough comparing the Claerbout III with the conventional imaging, Claerbout II, for one-way waves. Okay? What that leads to in terms of the amplitude, there is something with the image that occurs with one shot record, that people then sum over sources just to reduce that inconsistency. Yes? Here, you integrate over sources to bring the source down. Nothing wrong with the integral over receivers. You follow? It's not. So you'll see explicit examples of the distinction between those two sums. Yes? So we're trying to get, so all you'll see here are differences where there is no structural complexity, just amplitude issues. Yes? There's another difference, as I said, if you have structure, what 3 provides. If there's an interest, our group can continue that. Yes? What's the difference between, let's say you have this, and you do a Claerbout II versus Claerbout III on this structure, yes? But at some point, this is to get your interest, yes? And then to collaborate. We're not going to, as I said, produce a Claerbout III anisotropic heterogeneous, understood? Only we will do that with people who are expert at it. We can't compete with that. So there's another point here. The definitiveness of that Claerbout III that we have now for two-way waves allows us to provide a very clear answer to what is the role of primaries and multiples in imaging. Okay? So you'll see that in a later talk. But right now I'll stop.